Welcome to section 6.3. In this section, we're going to be pursuing further applications of integration into the field of business and economics and finance. So we're not going to spend too much time on these topics because this is the end of the chapter, but we want to introduce some new formulas that allow us to perform some of these financial calculations. We're going to see how integration plays a role in this, and then we're going to finish up chapter 6. So let's dive right in. So if over some interval with t going from 0 to capital T, money flows continuously into a pool at a rate approximated by the function f of t in dollars per time period, and if the money is reinvested in a non-interest earning account, then the total amount of money A in dollars accumulated at the end of t years is going to be calculated by taking the integral from 0 to capital T of f of t dt. So we have little t as our variable that represents time, and capital T is a specific value that represents the stopping time. Okay, so you can see I have a little diagram for us over here. So we've got our function f of t, okay, that is talking about our continuous money flow. The value goes from 0 to t, so that's how far time passes. And then this area down here, this is going to be the amount of money accumulated over the time from 0 to t. Right? So calculation-wise, there's nothing really that new here. You're taking the integral of a function. All that's really changing is the context. So let's take a look at an example. So revenue flows continuously into a retail operation at the constant rate of $128,000 per year. As the money is received, it is placed in a non-interest earning account. Determine how much money has accumulated in the operations account at the end of a 3-year time period. So the amount will be the integral from 0 to 3 of 128,000 dt. And that's simple enough to integrate. It's a big number, but it is just a number. So it just picks up a variable evaluated from 0 to 3. We get 384,000 for our answer. So in the context of the scenario, we could say if money is deposited at $128,000 per year in a non-interest earning account, the amount accumulated after 3 years is $384,000. Now, one thing to note about this calculation, because you have a constant amount coming in every year, you really didn't need an integral to do this in this particular case. So an integral was not necessary. If we knew that we had 128,000 coming in every year and it's not earning any interest, over 3 years, 128,000 times 3 is 384,000. So this is basically the calculation that we're doing. In this particular case, it was a constant function, so we could have just drawn that horizontal line and found that rectangular area. But obviously the integral is going to be much more useful when we have functions that are not just horizontal lines. When P dollars is invested at an annual interest rate R that is compounded continuously, the total amount A of money that will have accumulated at the end of T years is given by the following formula. So this one we are earning interest. Okay, so we're putting in P dollars to start. We earn interest at a rate of R, and then it's compounded continuously. And we're looking for the total amount of money at the end of T years. This is a formula that you might have seen before. You probably have seen it at some point. But this is P equals, oh, sorry, not P equals. You wouldn't have seen that formula before. It's A equals P times E to the RT. So this is often what we call the PERT formula for continuously compounding interest. Okay, so P is the initial amount or the principal amount. That's why it's labeled P. E to the RT, we use the natural exponential function E when we're dealing with continuous growth. And then R is the interest rate. T is the amount of years that have passed. So for example, we're taking that same $128,000. So if a one-time lump sum investment of $128,000 is made into an account paying 7% interest, compounded continuously, the amount of money that will have accumulated at the end of 3 years is A equals 128,000 times E to the RT. Be very careful. 7% does not mean that R is 7. 7% is actually equivalent to 0.07. It's equivalent to that decimal. So this is 0.07 times 3. This is something we would need a calculator to do. And we would end up with $157,910.79 approximately. So in this case, we put in $128,000 and just leave it there to grow interest for 3 years at 7%. And we end up making almost $30,000 out of that. We end up at almost $158,000. The next thing we're going to talk about is the concept of future value. So the amount or future value, A, of an annuity at the end of N payment periods is approximated by the following. So that's the integral from 0 to N of the PERT formula, P e to the RT dt. So the future value is A. N is the number of payment periods. P is the number of dollars invested at the end of each payment period. R is the interest rate per time period. And the integral measures the value of the investment in the future. So our value in the future, which obviously is why we call it future value. So we have continuous growth being extended over N payment periods, okay, with dollar amounts being invested in each pay period. So let's take a look at an example that we can try with this. So suppose at the end of each month for 6 months, $100 is put into an account paying 6% annual interest compounded continuously, except for the last $100, which earns no interest at all. Each $100 earns interest over a different period of time. Approximate the future value of the annuity over a 6-month period and over a 20-month period. So at the end of each month, they're putting $100 into this account, and then it's going to start earning interest. But the problem is, right, you're going to pay $100, and then it's going to start earning 6% interest. Then you're going to put in another $100, and it's going to earn 6% interest, but this one is going to earn also another 6% interest. And then you go to the next one, it's going to earn 6% interest, but so is this one, and then also so is this one. So each one is going to earn different amounts of interest as we go through the process. So calculating this manually is a nightmare. We want to go ahead and use this future value calculation to do this. So in order to set this up, so we're going to have a equals the integral from 0 to 6 over the 6-month period. And we're going to have P is that amount being put in every period. E to the RT. Now we're going to have to be very careful again. A little caveat here. This 6% is annual interest. So when we're talking about the interest being added on here, the interest being inputted is being inputted each month. Okay, so we're not taking 6% per month, it's 6% per year. So we need to get the monthly interest rate out of this, which is a simple enough calculation. You take the 6% annually and divide it by 12 months. And that's going to give us 0.005. So that works out to 0.5% every month. Okay, so instead of this being 0.06 up here, it's going to be 0.005 times t dt. Now we take the antiderivative of this. So remember, the antiderivative of the e expression will be itself again. So there will still be an e to the 0.005t up here. But because of this 0.005 attached to the t, we need to not multiply by 0.005, but because we're undoing the derivative, we need to divide by 0.005. And that's going to make this number balloon up to 20,000. And this is evaluated from 0 to 6. So we get 20,000 times e to the 0.03 minus e to the 0. You have to be very careful. I feel like I'm saying that a lot. Just in general, we'll just be careful because e to the 0 is not 0, it is 1. So that is going to change the value slightly. And we end up with this being approximately 609. So we can say the future, oh, that's not how you spell future. Future value after 6 months is $609. So over this 6-month period, they put in $100 at the end of each month, and it earned a little bit of interest. So by the end of the 6 months, they have $609 in there. So basically they made $9 in interest over that 6-month period. Now for part B, we're going to do the same thing, but over a 20-year period. Now, all of the calculations we've been doing here are in terms of months, So if we want to do this consistently, we're going to need to convert this into months. So 20 years times 12 months in a year is 240 months. So we're going to get the integral from 0 to 240 of the exact same formula. So the antiderivative is the same. The only thing that's different is the evaluation. Oops. So we end up still 20,000 times e to the 1.2 minus e to the 0. That is approximately 46,402.34. So the future value after 6 months is $609. They gained an extra $9 in interest. The future value after 20 years is $46,402.34. So a major step up, but remember they've been putting in $100 a month for 20 years. So there's a reason why this number is so large. That doesn't mean that they've earned now, $40,000 in interest. They've put in most of that money themselves, but they have been gaining interest for a much longer time as well. Right. So in addition to future value, we can also talk about the concept of present value. So to find the present value of A, we use the equivalent formula, P equals A e to the negative RT. So compare this to the one that we were already using. That's A equals P e to the RT, like that. These are equivalent to each other. It's just this one we solved for P, this one we solved for A. So they are consistent with each other. We're just looking for different information. So in the previous cases, we knew how much went into the account initially, and we were trying to solve for the final amount. In this case, we know the final amount that we're looking for. We're trying to find how much should go in now to make that amount in the future. Okay, so this tells us the amount P that must be invested now so that the amount A will be accumulated in the future. So we're looking at this backwards, basically. Instead of saying, here's how much I'm putting in now, what will it be later? I'm saying, here's what I want it to be later, how much should I put in now? So for this example, how much money should be invested now at 8% interest compounded continuously so that $15,000 will be available in 10 years? So we're going to have P equals 15,000 e to the negative 0.08 times 10. And not much more we can do with that except plug it into a calculator. We get $6,739.93. Okay, so in words, if $6,739.93 is invested now in that account, it will be worth $15,000 in 10 years. Okay, so this is a pretty practical question. This is the kind of thing that you can do, like what parents will sometimes do with like college funds for their kids. You know, they try to invest a little money when the kid is born so that by the time they get to college, there's a larger sum in there. So, you know, for example, if they knew they wanted to raise 15K, and they're like, okay, you know, they're going to college in 10 years. How much do I need to put in now to make sure they have 15? And that would be the amount given that interest rate. So this is future and present value. Now, to add an extra kind of wrinkle into this process, if f of t is the rate of flow of money into an account that pays an annual interest rate R compounded continuously during some time interval from 0 to t, then the future value of the income stream is going to be e to the r capital T times the integral from 0 to capital T of f of t e to the negative rt dt. So in this case, instead of having pe to the negative rt, or pe to the rt, the p is coming from here, okay, and it's based off of the function and then the amount of time, of course, that's passing. And present value is just going to be the integral from 0 to t of f of t e to the negative rt dt. So you can see that the present value formula lies within the future value formula. So remember that the formula, the original, like this, where this is the initial amount that gets put in to the account, well, that is this. Okay, so this is the P, this is the present value of the income stream. And then when we multiply that by e to the RT, that gives us the future value. That's the final value after it has accumulated its interest. Okay, so we're still working with the same types of formulas, but obviously the integrals give us a little bit more power in what we can calculate, and now we're incorporating functions and formulas, not just single numbers, okay? So let's try an example with this so we can see kind of how this works. So a company can buy a machine that is expected to increase the company's net income by $10,000 each year for the 5-year life of the machine. So we've got $10,000 each year for 5 years. The company also estimates that for the next 5 years, the money they invest from that continuous stream will earn 7% compounded continuously. Find and interpret the following. So the total amount of money produced only by the machine over its 5-year life. Okay. So the total amount produced only by the machine over its 5-year life. This is like what we started the chapter with, or the section with. And we really don't even technically need an integral to do this, but we can. So the machine is generating $10,000 a year for 5 years. There's no interest being calculated on the machine's value. So this is the integral from 0 to 5 of 10,000 dt. So that's 10,000 t from 0 to 5. So that's $50,000, which again is just $10,000 a year for 5 years, right? 10,000 times 5. Then it wants us to find the future value of the income stream and the present value of the income stream. So we already have a lot of the pieces that we need, right? We know the time is 5 years. We know the interest rate is 7%, so 0.07 for R. And we know this investment is $10,000 each year. So for our future value, we get e to the RT times the integral from 0 to t of that function. In this case, it is just 10,000. It's a constant. Excuse me. Times e to the negative RT, and that's little t, dt. So let's see, this is going to be e to the 0.35 times e to the negative 0.07t, and then we're going to divide by negative 0.07, because again, we're taking the antiderivative, so that's 10,000 divided by negative 0.07 times e to the negative 0.07t, evaluated from 0 to 5. And I'll go ahead and just cut to the chase on what that number is. It's approximately 42,000. Oh no, it's not. Sorry. I'm looking at the wrong spot. 59,866.79. Okay. So right now, the machine over the next 5 years will earn the company $50,000. If the company uses the income stream to then invest, they will earn $59,866. Now, for the present value of the income stream, we're asking the question, how much needs to go in now in order to earn this amount? So for present value, it's basically just the integral portion of this. So really, we've kind of already done this calculation once, just with this extra piece in front of it. So this one gives the other number. So this is $42,187.42. So now it's asking us to use these values to determine the conditions under which the company should and should not buy the machine. So we have the amount of money produced by the machine, we have the future value of the investment of that money, and then the present value of the investment of that money. So what this means is that if the machine sells for more than $42,187.42, then the company should not buy it, because they can generate the same future value by simply taking that $42,187.42 and putting it into a 7% interest earning account for 5 years. Okay, so this is our present value to yield that future value. If the machine costs more than this, then that means you're going to get the same future value out of it, but you're going to spend more on the machine than you would on just investing that money, right? So if the machine costs $45,000, for example, you're still going to net the same result, but you had to spend an extra $3,000 to get there using the machine. Whereas this way, you only spend $42,000 and you get the same future value. And on the flip side of this, if the machine sells for less than $42,187.42, then the company should buy it because it can generate the same future value for a smaller current investment. All right. So just to recap kind of everything that just happened here. So the company, if they buy this machine, it'll produce $10,000 a year over 5 years. Those $10,000 a year then get invested into an account and they earn some interest on it. So they're going to get $59,866. Okay, that's using $50,000 from the machine and then an extra $9,000 from the interest that they earn. Instead of doing all of that, they could just take this amount of money, $42,187.42, invest that in an account instead of buying the machine, and they will get the exact same amount of money. Okay, so buying the machine and earning interest off that, or investing this money and earning interest off of it, are the same. The outcome is the same in both of these cases. So if the machine costs more than this investment, it doesn't make sense to spend more than this on the machine just to get the same number out again. But if the machine costs less than this, like if I can get the machine for only like $30,000, I'm still going to get out my $59,000 and I could save a lot now rather than spending extra on the machine. So the conclusion that we draw is purely based around this present value, because both cases will yield the same value in 5 years, and it's just a matter of which one saves us money now. So obviously a lot going on with these examples. And like I said, we're not going to be focusing too much on these topics going forward. This is just another application, another way you can see this stuff used. The concept of exponential integration obviously is important to us in calculus. And then we can apply all these different formulas in the context that they're needed. So, but that brings us to the end of section 6.3 and to the end of chapter 6. So I will talk with you all in the next one.